Hello, friends. Here are all of the lectures from dynamics in our way that we break it up. This is Unit 2. I also took the drag force lessons and I put them in here as well. In the course sequence, I saved those for Unit 4 because it's in Unit 3 that we introduce integrals. So if you haven't gotten there yet, you can stop before you get to that section. All um, the notes are in the description below. So buckle up, enjoy. It's a long lesson, but it's absolutely foundational and use it in all the rest of physics, right? You might even say that this is physics and everything else in physics is an analysis of forces.
Okay, now we're into Unit 2. Unit 2 is really all about forces, and some of this will be review, some of it will be kind of new, the way that we approach this stuff. We are going to start right away in 2 dimensions, and let me say at the outset that free body diagrams are very, very important. I talked before about drawing the diagram. Always draw a picture, a diagram, something you need to picture it, but that's also true for free body diagrams. The last 2 years on the midterm, there was an open-ended question, a real AP open-ended question, and both years, most of the class got it wrong because they made one little mistake in how they drew the free body diagram. If you can draw a good free body diagram for each of the objects in the system, right, or for the whole system, whatever it is, that will greatly simplify the problems. Also, a lot of times, even if you're not asked to draw a free body diagram, drawing the free body diagram might get you some points. So it's always worth it to do a quick free body diagram. And we'll talk about those rules in a little while, but the basic rules are, 1, there's one object for each free body diagram, 1. And it's a box, a circle, or a dot, and the lines always come from the box, either from the center or from the surface, but they have to be touching the box if they're on the surface. There have been debates as people are grading the AP tests, if there's that much space between the box and where the arrow begins on the force arrow, do they give them credit or not? So, and then it'll depend on that year who's in the room and what the graders decide about that. But free body diagrams are very, very important, and it may have even been an issue for you on the summer assignment. So make sure you pay attention. Okay, so the first unit was all about motion, describing motion. That's all we've done. Now we want to say what causes motion. What causes a change in motion? And what is a change in motion but acceleration? So unbalanced external forces create acceleration. Right? There can be external forces, but those don't necessarily create change in motion, because if they balance each other out, then the acceleration will be 0. That's why the classic formulation of Newton's second law, objects at rest stay at rest, and objects in motion stay in motion unless acted on by an external force. That's Newton's first law. That's not necessarily true, because there can be external forces and the object still remains at rest or remains at a constant velocity. So we need to keep in mind what we mean that we're talking about the net force. Classical mechanics, that's what we're talking about here. It's valid for objects that are much larger than atoms and where the objects are traveling much slower than the speed of light. When you're dealing with really tiny objects, that's when you need quantum mechanics, and we're not doing that in this course. And if you get things faster than the speed of light, or not faster, that's not possible, but close to the speed of light, then you need special relativity, and we're not doing that in this course either. Some special relativity is covered in AP2, but if you're watching this video, then you're not signed up for that course, so too bad. Force. So force is a vector, magnitude and direction. Direction matters for a force. Keep that in mind. It's an interaction between two bodies, right? A body and its environment. What in the environment? Right, some other object. So whenever you draw a free body diagram and you're drawing the arrows, you got to think, what is the object that's exerting this force? And so the sum of all forces acting on the body is the net force. If the net force is 0, then it's 0 acceleration, it's a constant velocity, and we say that the body is in equilibrium. And for now, we're going to call it equilibrium. Later on, when we introduce rotation, then we would say this has translational equilibrium. That's linear movement, as opposed to things rotating. Right now, we're dealing with point-like objects, and so we're talking about translational equilibrium. Right? Newton's first law, if there's no net force, so there can be forces, but just 0 net force, then the object, if it's at rest, it remains at rest, but if it is moving, it'll have a constant velocity. Second law, F net equals ma. This equation is the nuclear reactor of all of physics. It's when I was in college with my other physics nerd majors, we used to joke, if you don't know the answer to the question, you just write F equals ma. That's it. And I've had students do that on tests. They write F equals ma. And sometimes they actually get a little bit of credit, like no other response, but they just write F equals ma. Turns out if that's one of the equations that you need to solve that problem, then you get a little bit of credit. Newton's third law. The idea here is that when two objects interact, then they exert equal and opposite force on each other. And it can be written as the force of A on B is equal to the negative force of B on A. Right? So you can switch those. Some vocabulary: mass. Mass actually can't be defined. It's that which is measured in kilograms. It's a fundamental characteristic of a body relating to how much stuff there is. System is a collection of two or more bodies. Right, so whenever you're looking at a problem, you want to decide what's my system here. Specify what are the objects that we're talking about. That'll be especially important when we get to energy, but it's also important here. External force is any force coming from bodies that are outside the system. Internal force are any forces between bodies inside the system. Net force, sum of all the bodies. Free body diagram, picture of one of the bodies and all the forces acting on it. There are contact forces, there are field forces. Contact, obviously things are in contact. Field forces, these can pass through empty space, things like gravity, electricity, magnetism. And the unit of force is a Newton, kilogram meter per second squared, which you should know. Different types of forces, gravity and weight. Right? Gravity is universal, it's anywhere in the universe. Weight, we're talking about the net force required to prevent a body from falling freely. Right? So weight would kind of be like the force the floor exerts on you to hold you up. Normal force is the force of the floor. That's the actual force of the floor. The weight is just the amount. Tension is a force from a rope or a cord. Sometimes even we talk about a spring having tension in it. Spring force, Fs, right? Force from a spring. Drag force, resistive force. We're going to get into that a lot more in a later unit because that involves some calculus that we're not quite ready to jump into yet. Friction, we have static and kinetic. Centripetal force, that stuff's going to get interesting. That is probably the most challenging part of this unit when we get to it. And important thing to note here, centripetal force is not, like the others, a kind of force where it's coming from an object. Notice centripetal force is just telling you the direction of the force. It's not specifying the object. As a result, centripetal force, this is important, listen, centripetal force never goes on a free body diagram. Never. Because in a free body diagram, you're drawing the interactions between the objects. So the centripetal force can be provided by, say, gravity, if we're talking about a planet going around the sun, for example, or it can be provided by a string, which would be a tension force. So there the tension provides the centripetal force. Right? Really what centripetal force is, it's a net force. It's a sum of forces together, because it could be more than one thing, creating that curved path. And then there are fictitious forces, things like centrifugal force, and we'll get into more of that later. Force of gravity, right? Newton posited that all bodies in the universe are attracted to all the others. And by the way, as a historical note, when he first said that, it made no sense. And it really doesn't make any sense to us still today, but we have equations that can describe it. The idea that something 90 million miles away, like the sun, could exert a force on the Earth, like how does it do that? Through empty space. And so that's why it was such a radical idea. It was such a huge leap. But that idea has led to a lot of advances and has been able to move science forward. So we use it. Right? Gravitational, it's a field force. The superposition principle applies, by the way. So if I have more than one body, that I add up the forces. Fields, right, means by which two objects exert forces on each other. So we talk about the gravitational field of the sun. That's, we say, oh, that's how the sun exerts a force on the Earth, which is true in terms of the way that we describe it. But fields are not things. You couldn't look through a telescope and see a field. You can't do, you can't look under a microscope and see a field. You can't touch and feel a field, right? It's a mathematical construct that we've developed to help explain these forces and describe them. And the force is always there no matter what the medium is. So we talk about tension. And so here, with our example here of the monkey in the elevator, tension in an elevator, right? For part A, if there's no acceleration, that means that the tension is equal to the force of gravity. This, by the way, is a free body diagram. Right. So then for B, if it's upward acceleration, that means that T is more than Fg. Oh, see that? I need to make that connect. Okay. So T is greater than Fg. And then if it's accelerating downward, that means that T is less than Fg. Right. Now, by the way, here, this doesn't mean it's staying still, this doesn't mean it's going up, and this doesn't mean it's going down. What we're talking about here is the acceleration. This one is not accelerating, this one's accelerating up, this one's accelerating down. But this one might be moving down, right? It might be moving down but slowing down. This one might be moving up but slowing down. The net force only tells us about the acceleration. It doesn't necessarily tell us about the velocity. So we need to keep that in mind. Translational equilibrium. This is what we're talking about, things moving linearly. If they're in equilibrium, then there is no linear acceleration. Right. Later on, we'll talk about rotational equilibrium, just so you can, why are we calling it translational instead of just equilibrium? The acceleration of the body is 0 and the velocity is constant. All right, this should be all very familiar. Equilibrant and equilibrium. If I want to know, if I have some forces acting on a body, and I want to know what force can I exert to put the object in equilibrium. Let's say it's out of equilibrium, but I want to say where would I add a force to put it into equilibrium. That force that you would add is called the equilibrant. Equilibrant, right? It's there in the notes. You might see that word, so it's important to know what it is. It is the force that will put a body into equilibrium. Okay, and so here's the idea. There's a force here. It's 3 by 4. Let me put it up on the board. Okay, so I've got these two forces. I'll describe this. So F net is 3 newtons J plus 4 newtons in the I direction. And I could probably switch that, but we'll leave it for now. So the sum of these forces, the magnitude, is going to be 5. So what force do I have to add to this in order to balance these two? Because right now this is out of equilibrium. If I add a 5 Newton force this way, then that'll work. So the equilibrant, F EQ, let's say the equilibrant force, it's just the negative of these two. I would need negative, let's say negative 4I minus 3J newtons. This is the force that's going to equalize this one. And then if I add this force to this situation, then I have an object that's in equilibrium. This is the equilibrant. Okay. Applying Newton's laws, draw a simple, neat diagram. Then isolate the objects, draw the free body diagram. This is general way of solving these. Assign the x and y directions. Right. Again, if you use the conventions that this is positive x, this is positive y, out of the page is positive z, then you don't have to specify. But you can change x and y, and we will do that at times, so we need to specify that. Then we use F net equals ma, solve equations, check for unknowns, and then we check for the reasonableness. So if I have the same force, example 1 now, acting on two bodies, m1 and m2, in a frictionless environment, producing accelerations of a1 and a2 respectively, find a2 as a function of a1. All right. This will be pretty simple. So what do I have here? It's the same force, F, and it's acting on two bodies, so m1 a1 equals m2 a2. So this is the mass and acceleration of one of the bodies, this is the mass and the acceleration of the other body, and they're both equal to each other because it's the same force that's producing both of these accelerations on these objects. And I want to find a2 as a function of a1. Well, here it is, right? a2 is equal to m1 over m2 times a1. That's it. That's all we're looking for in this problem. And so then example 2, let's take a look. So we have two forces. All right, so here it is. This is the free body diagram. It's a 5 Newton body, and there is a 10 Newton force this way, and then there is a 12 Newton force going this way. All right, right now this is a free body diagram. In order to solve this, of course, what I have to do is now get rid of these and find the components, right? So this is going to be, if this is 45 degrees, right, this is going to be 10 sine 45. That's going to give me 7.07 newtons. Now, right away, what I've done here, this is no longer a free body diagram, technically, because I'm breaking up this. This I would do in a separate drawing if I was asked for a free body diagram. All right, now this also is going to be 7.07 newtons, and then I can get rid of this one. All right, break it up into the x and the y. Now this one I'll also break up into the x and y. So 12 sine 135, 12 cosine 135. 12 cosine 135 gives me negative 8.49, and or cosine 135, and 12 sine 135 gives me 8.49 that way. Okay, so now I just add up all the forces. So the net force in the x direction is 7.07 minus 8.49. So that gives me negative 1.42 newtons, and the net force in the y direction is going to be 7.07 plus 8.49 minus 5. Right here, 2 up, 1 down, and so that gives me 10.56 newtons. Okay, so then we can say that F net, I can write sigma F, is negative 1.42 I plus 10.56 J newtons. And that's part A. Part B, what I'm going to do here is erase this now and go up. B is asking for the acceleration, and so I can express the acceleration this way. A, right, these are vectors so I can have the arrows over them. A is just F over m. So this is going to be negative 1.42 I plus 10.56 J over the mass. We're going to say the mass is 0.51 kilograms. And so the acceleration vector, now I need to get my calculator out. So this is going to be negative 2.8 I plus 20.7 J meters per second squared. All right, so that's part B. And then part C asks for the equilibrant. The equilibrant force, again, is just going to be, so FEQ is going to be 1.42 I minus 10.56 J. Again, what this means is if you were to add this force to the situation that's already there, then the whole body would be in equilibrium, and that would result in an acceleration of 0. And I think that's it for this first packet. Okay, now we're into the second section of Chapter 5. And so, again, as a review, the procedures for applying Newton's laws: draw a simple diagram, draw the free body diagrams, assign x and y, and then look at the net forces in each direction. So now what we're going to do is we're going to look at pulleys, We're going to look at Atwood's machine, which you probably remember from last year. For now, we're doing frictionless, massless pulleys. Towards the end of the mechanics unit, I think unit 5, we will have pulleys with mass. I know you've been dreaming about that and looking forward to it, but that's going to have to wait for now. So the question is, find the tension in each massless string for these pulleys in equilibrium. Here's our first example. Let me see if I can find a black marker. All right. So here's our diagram. So this is just some force here, and then there's that thing there. Okay, so here's the free body diagram for this one. This is 5 kilograms. There is a string pulling up and the force of gravity pulling down, right, Ft. And it's in equilibrium, meaning that the net force is 0. And so here, if this is 50 newtons, this is 50 newtons. So the tension in the string is 50 newtons. That means this is going to be 50 newtons as well. So 50 newtons, 50 newtons. Free body diagram for the pulley now looks like this. I've got two 50 newton forces pulling down. That means if this is in equilibrium, that's got to be 100 newtons. Okay, pretty simple example there. What about B? So now in B, again, we've got the pulley, and now we've got a weight hanging there, and then another weight here, and then a string pulling down. Again, if it's in equilibrium, this object is going to have 50 newtons pulling down on it. That means the tension in the string has to be 50 newtons. That means this one, the tension here is 50 newtons. So now let's take a look at this particular block. It's 2 kilograms, meaning there's a force of gravity of 20 newtons on it. Then there's this other tension force, whatever that is, and there's an upward tension force of 50 newtons. 20, 50, so that means this has to be 30 newtons. Again, I've got two 50 newton forces pulling down on the pulley. That means this has to be 100 newtons in the tension pulling up there. And then this pulley, right, so this is pulling down, this is 5 kilograms, and then it's attached like this, right? So if this is 5 kilograms, I've got 50 newtons of gravitational force pulling down, this is 50 newtons pulling up. That means these have each got to be 25 newtons, like that, okay? These are pretty simple examples. Hopefully they're not causing you too much stress at the moment. Let me see if I can find a better marker. Okay, so now again, let's take a look. These are 5 kilograms hanging from each end. That means it's 50 newtons pulling down here and 50 newtons pulling down here. This one throws everyone off because they see this and they must say, oh, that means the tension here is 100 newtons. But it's not. If the tension was 100 newtons, then this would not be in equilibrium. This would be accelerating upward. The tension here has to be 50 newtons, 50 newtons, 50 newtons. Okay, that's for those. Now what about these guys? What is the force here? Well, if this is 45 degrees, let's take each of these like this. I've got 50 newtons pulling down, and I've got 50 newtons pulling that way. That means there has to be another force, 50 root 2, assuming an angle of pretty much, oh, it has to be, yeah, 45 degrees because these two are pulling that way. This is the equilibrant for these two, and we know everything's in equilibrium, and so the force on the pulleys is 50 root 2 outwards. And this thing is exerting a force 50 root 2 newtons that way. All right, now this is the same kind of thing as in E, except that E now is just taking this situation and there's a wall to which this string is attached. Again, this has to be 50 newtons in order for everything to remain in equilibrium. All right, and we just keep adding to the complexity here. More and more pendulums, not pendulums, wrong unit, pulleys. All right, so what we're going to do is we're going to start with the thing that has that we know this is 50 newtons, so it's pulling down 50 newtons. That means this has to be 50 newtons. The tension everywhere in this string is the same. That's a general rule, that if the pulleys are massless and frictionless, then the tension everywhere in the string is the same. And so if this is 50 and 50 pulling down, this is 100. If this is 50 and 50 pulling up, then this is 100 as well. Whoops, that's not 100. 100 newtons pulling up. All right, and what about this one? Okay, now here I don't know the tension in the string here, so I can't know that or that. I need to start here with the 6 kilogram. This is 60 newtons of gravitational force pulling down. That means the tension everywhere in this string is 60 newtons. Well, here, and now there's a weight here, right? This weight, let's take a look at this one by itself. It's got a 60 newton force pulling down. It's got 20 newtons of gravitational force. That means the upward tension has to be 80 newtons. All right, so this is 80 newtons here. That means this is 80 newtons. And again, this block by itself has 10 newtons pulling down, 80 newtons pulling up. That means this has got to have 70 newtons pulling down here in order to balance all of that out, right? And so this is going to be 70 newtons. All right. And so now these tensions, 60 and 60, this is going to be 120. This tension is going to be 120 newtons. This one now is going to be 160 newtons. Okay, and that's it. Now we're going to look at Atwood's machine. Here's your derivation that you're going to need to know. All right, so let's take a look at this. If I do the free body diagram for each of these guys, here's mass 1. That means this is going to be m1 times g, and this is ft1. This free body diagram for mass 2, pulling down is going to be m2g and ft3. Okay, now this is going to be, if we assume that m2 is more massive, let's say that this one is accelerating upward, this one is accelerating downward. Notice I didn't put these on, like I didn't attach these. Typically motion arrows, we want to draw just a little bit off to the side, telling us about the motion of that object, right? So the thing that I know, and this is really the link when solving a lot of these really difficult problems, the acceleration is the same. These things are attached by a string, so the magnitude of acceleration is the same. And picking the direction of acceleration is going to be big as well. And so now I can write some equations. Okay. And by the way, we're going to consider this way, like up here and down here, as the positive direction for the acceleration. So ft1 minus m1g is going to be m1a. Okay, and then ft3 minus m2g is going to be m2 times a. You know what? I'm actually going to flip this because this m2g is more m2 times g, sorry, minus ft3. Now they're all equal to a. And so what I'm going to do is I'm going to, let's see, can we solve for g? Oh, well I know that ft1 and ft3 are the same. That's going to be the link here. So ft1 equals m1a plus m1g, and then ft3 is going to be m2g minus m2a. These two things are equal to each other, and so m1a plus m1g equals m2g minus m2a. Looks good, right? And so now we're going to bring out the m1, or let's gather the g's together on one side and the a's together on one side. So m1a plus m2a equals m2g minus m1g. Factor out. So we're going to have m1 plus m2a equals m2 minus m1 G. And now I'm solving for A, right? So let me just bring this back up here. So A is equal to M1 or M2 minus M1 over M2 plus M1 times G. And that's it. This is the formula for the acceleration of the blocks in this type of situation. So now the what ifs. What if M1 is equal to M2? Well, if M1 equals M2, then the acceleration is 0. And what if M2 is much, much greater than M1? If M2 is much, much greater than M1, then this basically becomes M2 over M2. We ignore the M1, and the acceleration is just equal to G. You have basically an object in free fall. Okay. And so now we have a modified Atwood's machine. Oh, by the way, we should do here to find the tension. What are these tensions? And we can find that by plugging this back into here. Ft1, or T, well, it's the same. So Ft1 equals, say, minus M1G. Or no, let's put it into this one. Better. Ft1 equals M1A plus M1G. So this A is now this thing, so it's M2 minus M1 over M2 plus M1 G plus M1G. Oh, of course I forgot this M1 here. All right, that's going to change this. So now this is going to be M1, M2 minus M1 squared over M2 plus M1. And then plus M1, M2 plus M1 squared over M2 plus M1 times G. Now when I add these up, these M1s disappear. And so I get 2M1, M2 over M2 plus M1 G. Right, so that's the tension now. Notice the 2. We're going to come back to that later. All right, now we're going to do the modified Atwood machine. So what does this look like? This is the same tension. So for this block, notice now this only has one force on it. So Ft1 equals M1 times A. Right, and now Ft2 minus M2G is equal to, you know what, let me do this the other way. Since I'm making this way positive, I'm going to make, since this is the direction of the acceleration, I'm going to make that the positive direction. So M2G minus Ft2 is equal to M2A. These are the same, so I'm just going to plug this into here. So M2G minus M1A equals M2A. Right, so let's see, M2G equals M2A plus M1A. So M2G equals M2 plus M1 times A. So the acceleration is M2 over M2 plus M1 times G. Okay, so that's it. And now let's take a look at what the tension is going to be. So if I have this tension, I plug this into here. And so this now is M1 times M2 over M2 plus M1, sorry, that's a 1 times G. Right, I got this, I plugged this back into here, and now I have that. That's what the tension is. That's pretty simple. Notice this has like a coefficient of 1 because there's one hanging mass. The other one was 2 M1, M2 times M2 plus M1. And so that's the derivation for the modified Atwood's machine. I want to show you a little bit of a shortcut for some problems like this that's going to be helpful where you see pulley problems. All right. Okay. what we're going to do is we're going to say this is the direction of the acceleration. And for what I'm going to do now is I'm going to pick both of these things as my system. Right? Systems are important. Before I was talking about systems, basically I was treating each block individually. Now I'm going to treat both of these blocks as a system, and I'm going to look at the acceleration of the whole system. Since they all have the same acceleration, I'm going to consider them one thing, and the acceleration of the system is just the mass of the whole system, or the force, external forces on the system, divided by the mass. So sigma F equals ma. What are all of the external forces on the system of both masses? Just this, right? m2g. And then now what's the total mass? The total mass of the system is m1 plus m2. And then since they're connected, they have the same acceleration. Notice now I get the same result as that other derivation. m2 over m1 plus m2 times g. The same thing works for the regular Atwood machine. Let's check it out. If this is m1, this is m2, what happened to tension here? We didn't include it. Why not? Because it's not a net external force. Internally, this tension cancels out. This tension is pulling in that direction on this mass and this direction on this mass in opposite directions of the acceleration, and so they cancel out. That won't always be the case. You may see a problem where the tension does not cancel out for some reason, or there might be internal forces that don't cancel out because of the direction that they're pulling and pushing. So watch out for that kind of thing. Make sure the internal forces cancel out. But here, this tension and that tension cancel out. Again, here, net F net equals ma. So what are the net forces? Well, if this is the direction of the acceleration, this force is pulling in the opposite direction, right? The gravitational force pulling down here. So we're going to say negative m1g plus m2g. These are the two forces. These are the only two external forces here pulling on these weights. Because the tension, again, cancels out. It's pulling up on this one, in opposite directions of the acceleration that we decided, so we're not including it. And then what's the total mass that's moving? m1 plus m2, and then times the acceleration. If we simplify this, right, just bring the m's together, get the g's together, so m2 minus m1, divide this over, m1 plus m2, g equals a. Same kind of thing, but it's a shortcut. But in order to do this, you've got to get the system straight. What's all the things that are moving, and then be careful about analyzing what are all the external forces. And that's it for this lesson. All right, now we're going to take a look at section 5.9b. And so here we're looking at normal force and multiple body systems, that kind of thing. So let's get started. Body's in contact with the surface. The surface pushes on the body with a force that is normal to the surface, right? Normal means perpendicular. And so in A, there's no applied force. The only thing that the surface is fighting against is gravity. And so that would be 50 newtons pushing up. That's the normal force. In B, you've got 10 newtons pushing down. And so that means that the normal force has to fight gravity and that 10 newton force. So the normal force in B would be 60 newtons. In C, there's a 10 newton force up. So that's relieving some of the force of gravity. And so the force of the surface is just going to be 40 newtons. What's up? Sorry for the interruption. Okay, and then D, for part D, there's a 10 newton force, but it's at an angle. And so there's only 5 newtons down, right? If you do 10 sine of 60, sine of 60 is 1/2, and so it's 5 newtons down. And so that's what the normal force is fighting. Gravity plus the 5 newton force from that applied force. And so the normal force is going to be 55 newtons. In an elevator with the monkey, if there's no acceleration, then the normal force is just the weight of the monkey. If the elevator is accelerating upward, then the normal force has to be more than the force of gravity. You know it this way. If this is the monkey, not the elevator, but the monkey, here's mg. If it's accelerating upward, that means that this force has to be more than this force. So the normal force is more than this. Again, that just means acceleration upward. That doesn't mean it's moving upward. It might be slowing down as it's coming down. And then if it's downward acceleration, that means that the downward force has to be more than the normal force if it's accelerating downward. If we were consistent, like this is the exact same problem and the exact same setup, but just a different acceleration, then these two arrows should be the same length. But in this situation, our monkey gained some weight. So I'll do that. Anyway, no friction on the ramp. This is a different type of situation where we have normal force. And let's do a little bit of geometry so we can see where this angle ends up. We're going to be doing this quite a bit later on, so let's just start it now. On the inclined plane, this is the angle theta, and so here's the block, whatever it is, that's there. So I want to know, this is going to be Fg equal, this normal force will be equal to Fg times something, right, sine or cosine of the angle. Well, if I draw a line here that is parallel to the bottom, then these are alternate interior angles. So this is also theta, right? And then I can draw a line downward. And so if this is theta, this angle here is 90 minus theta. But then I can also draw this. So this, excuse me, this now is perpendicular to the ramp. So if this is perpendicular to the ramp, then these two add up to 90 degrees. So this is theta. Right? And so this is the one that is opposite. So that's the angle. So here's theta. This then is Fg cosine of theta. And this parallel force pulling down is Fg sine theta. But we're looking at the normal force right now. So it would be that. If I add a force that's parallel to the surface, something here, Fa, this doesn't affect the normal force at all because it's perpendicular to the surface, or rather parallel to the surface and perpendicular to the normal force. And so Fn is still Fg cosine of theta. But now if I have some force pushing in this way, right, some Fa, then I can break this up into components parallel and perpendicular to the surface. And this is theta, same as this. So this one is Fa cosine theta. And this is Fa sine theta. That means the normal force has got to be Fg cosine theta plus Fa sine theta. Because Fa sine theta is this component. It's the component that's pushing into the surface. So the surface has to work against that. Again, Newton's third law, when we're looking at these things, two bodies interact, the forces of the bodies on each other are equal in an opposite direction. So if I have two bodies that are pushing against each other, whatever the force is on mass 1, so here's 1 and here's 2, let's say that they're attracted to each other, because it doesn't specifically say here. If this is the force of 2 on 1, then this is the force of 1 on 2. They're equal in magnitude, just opposite in direction. And you know, if we look at whole systems, if we make the system big enough, then everything is there. All the objects are included, all the forces, they're all internal. So how does anything ever move? There's a question that I've seen. Imagine that you're hooking up a horse to a cart, you're getting ready to go, and the horse turns around and says to you, you know, according to Newton's third law, no matter how hard I pull on the cart will pull back on me with equal and opposite force. So it's impossible for us to go anywhere. So you may as well just unhook me from this cart, and we shouldn't really do any work. How would you answer the horse if he said that to you? You know, first of all, you check your sanity, make sure you're feeling well, and then you're talking to a horse. But the idea is that what we're looking at is the net force on the object. So if the system is the horse and the cart together, then you're looking at all the external forces on that system. And if you're looking at just the cart, then you look at the forces on the cart. Why does this work? It works because we pay attention to systems. What are the objects in the system? And we look at the external forces. We draw free body diagrams, and it all makes sense. So if this is the cart, let me make a little space here. If this is the cart, what are all the forces on the cart? We've got the force of gravity, we have the normal force. These two should be the same. And then if this is the force of the horse on the cart, as long as this is more than this, the force of friction, or any other forces that might be there, then the cart will accelerate forward. If we want to see, the thing is, Newton's third law pairs of forces are always drawn on separate free body diagrams. They never go on the same object because they're always exerting forces on the other objects. All right, so here's an example.
Attention sophomore.
They're doing an announcement.
Your Six Flags forms are today in C hallway.
Okay, that was informative. And the next thing, we have these 3 blocks, like this. Here's M3, here's M2, and M1. This is 3 kilograms, 5 kilograms, and 2 kilograms. And there is a 30 Newton applied force on this frictionless system. Okay, so we want to know, find the applied force and all forces between the blocks. Oh, sorry, we don't know this yet. I just wrote that in. If the frictionless system accelerates at positive 3 meters per second. So there's acceleration here of 3 meters per second squared. Okay, so how do I find what the applied force is? Well, again, sigma F equals ma. So what is the total mass that's accelerating here? Because this force is accelerating that whole thing. So F is this total mass, which is 10 kilograms, times 30 meters per second squared. And so the force is 30 newtons. Really simple. Now I want to know, what's the force that 3 exerts on 5? Right? M1 exerts on M2. Well, if that's the case, so let's write it this way. The force of 1 on 2, let me write it that way. Force of 1 on 2 is equal to whatever this total mass is, and this total mass is 7 kilograms, times the acceleration, which is 3 meters per second squared. Sorry, this should be 3. I jumped ahead of myself there. 3. And so this is 21 newtons. Okay, that's the force of 1 on 2. What about the force of 2 on 3? Well, this force is accelerating just this one mass, which is 2 kilograms. And then the acceleration is 3 meters per second squared. And so that comes out to 6 newtons. Okay. Now there's a trick here, and the trick comes in this way. If I want to know the force, say between these two, what I do is I take the total force, this total force, and I multiply it by the ratio of the mass that's being accelerated to the total mass. So the mass that's being accelerated here is just 7 kilograms. And the total mass is 10 kilograms. Right? What does this come out to? 30 divided by 10 is 3 times 7 is 21 newtons. Right? And now notice that's what we got down here as well. This trick works because everything has the same acceleration. Same thing for this, when we're doing this. I can analyze all these as one single body because they all have the same acceleration. Same thing in example 2. Let's take a look at this. All right. In the first situation, the system is moving upward at 3 meters per second, and that means it has 0 acceleration. That means the net force is 0. Right? So the net force is 0. What are all the forces? Well, there's the force of gravity, negative force of gravity, plus the tension equals 0. So we're looking at this tension, and what I'm going to do is this. going to say this is T1, T2, T3. All right, so we're looking at T1. So let's look at T1 first. So T1 is equal to Fg, and T1 is holding up all of these masses, right? So T1 is equal to m1 plus m2 plus m3 times the acceleration due to gravity, times 9.8 meters per second squared. So that's T1. T2 then, it'll work the same way. It's just T2 is holding up these two masses. So T2 is m1 plus m2 plus m3, or sorry, not m3, m2 times 9.8 meters per second squared. And then T3, of course, is only holding up that last mass. Sorry, this should be masses 2 and 3. And this one is only holding up m3 times 9.8 meters per second squared. Okay, that's part A. Part B, though, in part B, it's accelerating upward at 3 meters per second squared. So now, this is not 0. I'll erase this for now. This is no longer just 0. Sigma f equals m total times 3 meters per second squared. And so, again, this is m total times 3 meters per second squared. So now this is Fg plus m total times 3 meters per second squared. Now this is m total right here, right? I can actually factor this out. Let's write m total times 9.8 meters per second squared plus 3 meters per second squared. Because this is mg, right? M total times g. So I factor out m total and I get this. So now all these answers are the same, except that instead of 9.8, it's all 12.8. Right? So that's part B. Part C, now it has a negative acceleration, right? So it's accelerating downward. What I'm going to do here then is make this negative, negative, negative. So this then just becomes negative minus 3 meters per second squared. And that's what I'm expecting, right? If it's accelerating downward, I'm expecting the tension to be less than the force of gravity on that. So the force of gravity is winning and it's accelerating downward. So this now ends up being 6.8 meters per second squared. Okay. Good. So now we've got 2 more examples. Let's take a look. All right. Imagine now in this situation, this force is 10 newtons. And so what I'm going to do first is kind of break this up. So for this one, I have this tension, right? That's the free body. There's also the normal force and the gravitational force, but we're going to ignore that for now. There's no friction. For this 1 kilogram, there's 10 Newton force up, and then I also have the tension pulling down, so it's the same as this. And then I'm also going to have this, which is going to be Fg sine of theta. That's the parallel force pulling down. Okay. And so they all have the same acceleration. Because this object only has one force on it, the net force is equal to ma. So that's the tension is equal to 3 kilograms times the acceleration. So now when I write the equation for this, the net force equals the mass times the acceleration. The net force is this, so the 10 newtons, minus the tension, minus Fg sine of theta. And if Fg is 10, let's use 10 for this. 10 is 10 meters per second squared as the value for g. And quick thing, notice if this is 10, the angle is 37 degrees. That means This is 37 degrees. 37 degrees, you should program this into your head. That's the angle of a 3, 4, 5 right triangle. That's the small angle on a 3, 4, 5 right triangle. So this is 10, this is 8, this is 6. You save yourself some calculator punching that way. Just remember, 37 degrees is the angle in a 3, 4, 5 right triangle. Trying to make it easy on you. And so then this would be 10 sine of 37 degrees, but it'd actually be 6. Right? So 6 equals m, which is 1, times a. But t is also this thing, right, 3a. So I can do 10 minus 6 was 4. So 4 minus 3a equals a. So 4 equals 4a. So the acceleration is 1 meter per second squared. Here's the other way to do this, all right, the way that I like a little bit better. It's something of a shortcut. What we did here was we used these bodies individually as separate systems and then found the thing that they had in common and substituted. That happens automatically if we take both of these as the system and I just ignore internal forces. What's the internal force between these two things? The tension. So sigma F equals ma. What are all of the external forces? Well, I've got the 10 newtons this way, right, pulling up along the ramp here. And then what are the external forces pulling against it? Well, just this, right? This Fg sine theta. So that would be 6 newtons equals, and then m, what's the total mass involved? The total mass is 4 kilograms times the acceleration. So this is 4 newtons equals 4 kilograms times the acceleration. So the acceleration, again, we get 1 meter per second squared. So you can see it works both ways. That way is shorter, it's simpler. But you need to understand how systems work and be able to analyze what are the internal, what are the external forces. So let's take a look at example 4. And now for this last example, this is a remake because I messed it up the first time. And here we go. What we have is this system with 2 blocks and a pulley in the middle. And we're going to do this the easy way, where the system is both blocks. Since the system is both of these blocks, we ignore the tension, because the tension is an internal force to the system of both blocks. When we write our Newton's second law equation here, then the only 2 forces I have are this, and I need to pick a direction. I need to guess at what the acceleration is going to be. So let's just guess that the acceleration is going to be that way. And so I'm going to make this my positive force. So this is Fg sine of 30, and I'll make this my negative force, Fg sine of 60, equals ma, and this mass is going to be the total mass of both blocks together. Now this block is 30 newtons. And this is 20 newtons. And they have a total mass of 5. So this ends up being 15 minus 17.3. So I end up with negative 2.3 is 5a. So the acceleration is negative 0.46 meters per second squared. All right, so that means that the acceleration is actually this way at 0.46 meters per second squared. And then to find the tension, what I can do is I can set up an equation for one of these guys. Let's say this one. And here is Fg sine 60. It's accelerating this way at 0.46 meters per second squared. And this is the tension. And so Fg sine of 60, which I know is 17.3, minus the tension equals the mass times the acceleration. And so the tension is going to be Fg sine of 60 minus ma. Right, solve that. So this is 17.3 minus 2 times negative 0.46, which I don't have. But if you do that, minus 2 times 0.46, you should get 16.4 newtons, about. So that's what the tension is in the cord, and the tension is going to be the same in both places. Okay, and that's it. Okay, so now we're on to Chapter 6. We're going to be skipping 6.4 just for your information. We'll come back to that later. That has to do with drag and resistive forces, and that's going to involve some calculus that we haven't learned yet. So we'll get back to this. So just a reminder about Newton's laws, what they are, and friction. Right? Friction occurs because no surface is perfectly smooth. If surfaces were perfectly smooth, there would be no friction. But also there's electrical force between all the atoms, right? Really tiny, and so that slows things down. And there are different types of friction. There's static friction, kinetic friction. There's also rolling friction, which we'll study later on. Not very in depth, but some. And there's drag and resistive forces as well. Static friction is friction when an object is stationary, it's not moving. That's the friction that has to be overcome in order to start the thing sliding. And kinetic friction is what you have when something is sliding. Typically, kinetic friction is less than static friction. So once you push it and overcome the static friction, then the friction is a little bit less and relatively constant as the thing is sliding. This should all be review from last year. And so static friction equations, the maximum static friction, that's when you use mu(s), the coefficient of static friction. And but static friction can be less than the force, the maximum static friction. Kinetic friction you calculate as mu k times Fn, and then rolling friction would be mu r, rolling friction, but you're going to see very few, if any, problems involving that. Most friction problems, right? Well, every friction problem, draw the free body diagram, right? The free body diagram, drawing the diagram is really important. If you think it, write it. You've got to have some type of illustration or diagram, because once you start adding a lot of forces, you want to be able to see where do all of these things go, right? What are the forces that are balancing out or not balancing out? And think, are these forces more than the force of gravity? The applied forces, are they less than, or the force of friction, are they less than the force of friction? What direction is the acceleration? All those types of things. And so all you're doing really is applying Newton's laws. So in the first example here, you have a rope, and we're trying to accelerate a 30 Newton box. I'm going to draw this out so we can see all of the forces and everything. Okay, so here's the information that's given to us. The thing to do now is figure out, I don't think, actually the normal force is not given to us, but we can figure it out from this. If this is 30 newtons, this now I'm going to break up. So this is going to be 10 root 3, is that right? And this is going to be 10 newtons. So if this is 10 newtons, this is 30, that means the normal force here is 20 newtons. And so this also is like 17.3 or so newtons. The maximum static friction, Fs max, is going to be 10 newtons because it's, now I know the normal force, I can say mu(s), which is 0.5 times the normal force, right? So 0.5 times 20 gives me 10 newtons. And the kinetic friction force is 0.2 times the normal force, which is 20. And so that's going to be 4 newtons. So the first question is, will the box accelerate, yes or no? What we're asking here really is this force more than the force of static friction? The answer is yes. This is more than this. And so we're not going to have static friction. This thing is going to be accelerating. And since it's accelerating, so the answer A we already did. B, will it accelerate? Yes. And justify your answer, we'll say the x component of the applied force is greater than Fs max. And then part C says if the box accelerates, the time required for it to travel 10 meters from rest. Okay, so then I want to know the net force, so I can calculate the acceleration. Yeah. Hey, what's up? Come on in.
Are we doing the cars today?
Yep.
All right, because I tried it yesterday, but me and Mark had just totally failed.
You'll have like a half an hour to work on it in class.
Yeah, we have stuff. We just
Okay,
sorry.
cool. No problem. You're good. Fix that. Okay, so the net force then horizontally is 17.3 minus 10, or sorry, minus 4. Get that right? Yeah, okay, so it is 4. Because this is 17.3, this is 4. So this comes out to 13.3 newtons. And then I can divide that by the mass. This thing is 3 kilograms. It's 30 newtons, and so that means it's 3 kilograms. So the acceleration is 13.3 divided by 3, and that gives me 4.43 meters per second squared. Since I know the acceleration, now I can calculate the time it takes, assuming it starts from rest. It says from rest, right? So delta x equals VIT plus 1/2 AT squared. This is 0, because VI is 0. I know the acceleration. I know delta x is going to be 10 meters, and so I'm just solving for time. Let me go up here. So the time is the square root of 2 delta x over a. It's a bunch of algebra. Quickly. This is 2 times 10 divided by 4.43. Take the square root, and you end up with 2.12 seconds. All right, so now we want to find the tension in the rope attached to the 5 kilogram box. All right, so let's take a look at the 5 kilogram box. What are the forces acting on the box? You've got the force of gravity, you've got the normal force, you've got, so if this thing is sliding this way, that means it's exerting a friction force on it this way. So here's the friction force, Ff. That's going to be equal to this tension force, because the tension is going to be equal to whatever this is, because this is just staying in equilibrium. It's staying in the same place, as being held there. And so I need to find this friction force. Well, this is mu times n, and mu, between all surfaces, as it says, is 0.2. So this is 0.2 times the normal force, which is equal to the force of gravity. And so that's going to be 50. So it's 10 newtons. Right, 0.2 is a fifth. 1/5 of 50 is 10 newtons. So that's the answer to part A. Now part B, the acceleration of the 10 kilogram block as it slides below the 5 kilogram box. Let's draw the free body diagram of this box. This has the force of gravity acting on it. It also has the force from this 5 kilogram box. So I'm going to write F5. Now the normal force is going to be these two things together. I've got 45 newtons from this applied force, and now I have this way, I actually have two separate friction forces. The friction force from the 5 kilogram box, so 5 friction, and then the force of the floor friction, or the ground friction. Okay, that's a lot of forces there. This is equal to 100. This is equal to 50. Okay, so this is just mg. This is the weight of this box, which was 50. The normal force then has to be 150 newtons. This friction force is equal to mu Fn for the 5 kilogram box, so that's the same as what this was. So this is 10 newtons. This is going to be the normal force on this box times the coefficient, so it's 0.2 times the normal force, 150. And so that 1/5 of that is going to be 30. So this is 30 newtons. This we know is 45. Okay. Notice I had to do all the vertical stuff in order to get this. So now the horizontal net forces are equal to mass times the acceleration. All of these are 45 minus 10 minus 30, because minus 10 minus 30 equals the mass, which is 10 times the acceleration. 45 minus, that's 40, so this is 5, equals 10 times a. So 0.5 meters per second squared is the acceleration. Okay, and now we want to know what is the acceleration of the box after it's passed out from underneath the other 5 kilogram box. So I'm going to do this over here, and there are actually a few things that change. All right, so I still have this 45 newtons. Doesn't say anything about that changing. I still have the force of friction from the ground, FGF. I still have the force of gravity, which is still 100 newtons. But now, notice I don't have this anymore. So the normal force now is only 100 newtons. That means the force of friction, I don't have this friction anymore. So this one is going to be 0.2 times 100. It's a different normal force now. So this is 20 newtons. So the net force equals ma. The net force, though, is 45 minus 20 newtons, minus this one, equals 10 times a. So this is 25 is 10a. So a is 2.5 meters per second squared. Okay. So we want to know at what angle will this thing start to slide. Okay. And we know that the coefficient of static friction is 0.5. Well, at the place where it starts to slide, that means that's the place where these two things are equal to each other. It's just at the point where this is going to break that. And so if I set these equal, Fg sine theta is equal to mu Fg cosine theta. When I'm solving for, let me get the thetas together, because really what I'm looking for is theta, right? How do I solve this? Well, if I can get sine and cosine together, sine over cosine is tangent. And so if I do this, Fg sine theta over Fg cosine theta is mu. Notice this cancels out, so I just end up with tangent of theta is mu s, right? And so then inverse tan of mu s is theta. So the inverse tangent of 0.5, I just plug that in as 0.5, gives me an angle of 26.6 degrees. And then part B, at what angle will the box slide down the incline at a constant velocity? Well, if it's in a constant velocity, that means these two are the same, except mu is just now mu k. So it's the exact same thing, except I'm just changing mu k, or mu s to mu k. So then for part B, inverse tangent of mu k, which is 0.2 theta. And so then if I plug in 0.2 for this, I get 11 degrees. Okay. Example 4 is similar to this, except it says that it's slightly inclined. And it's a 10 Newton box. We want to know, calculate the acceleration of the box that the plane is oriented at. 10 degrees, 20 degrees, 30 degrees. So it's kind of like what we had before with these angles. Right? It's all the same situation, the same coefficients of friction. That means that still I have, if it's less than 26.6 degrees, it won't be sliding. So for A and B, not moving. We incline it to 10 degrees, it hasn't gotten past this yet. Incline it to 20 degrees, still hasn't gotten past this, so not moving. A and B, not moving. C is 30 degrees. Once it's at 30 degrees, now it has broken maximum static friction, and now I have kinetic friction here. And so I'm looking for the acceleration, so net force is ma. What are the net forces on it? Fg sine theta minus mu k Fg cosine theta, and that's equal to ma. Right. What we can do here also is get rid of the m's, because this is really mg, right? mg. These cancel out. And so then I now have g sine of theta minus mu k g cosine theta equals A. It's just one less step that we need to worry about here. So this is going to be, we're at 30 degrees, right? So this ends up being, here I actually use 9.8. Right, 9.8 sine of 30 minus 0.2 times 9.8 times cosine of 30. You put that in your calculator, you get 3.2 meters per second squared. And that is it. That's the last example. The rest of these are kind of review. The next one talks about how the direction of the acceleration might not be obvious, so what you do is you guess, and then switch the direction if you get a negative answer, like what we did in the last packet. These on drag force, resistive force, and then centripetal force, these are previews. We're going to do some stuff on centripetal force as part of this unit. The drag and resistive force we're going to come back to later in another unit. Circular orbits, that we're going to get into quite a bit in our last unit in the mechanics section. So that's it for this lesson. We're skipping 6.4, we're going to come back to that later, but now we're getting on to 6.5. And 6.5 is where things get interesting, because now we're talking about circular motion. The key idea with all circular motion is this, that we want to point the direction of the acceleration towards the center of the circle. As a result then, we want to break up all the forces into components where we can analyze the part of the forces pointing towards the center of the circle, right? We have some motion, it's a circular, it's a curved motion. Acceleration is towards the center. The word centripetal, by the way, means center seeking. Centri, meaning having to do with the center, and then pedal comes from the Latin word petire, which means to seek. So it's the center seeking acceleration. And so some basic formulas that you should know, right? 2 pi r over t, 2 pi rf, and the period is the reciprocal of the frequency. That should all be reviewed. What we're talking about here is, at least for now, is uniform circular motion. I think we will get to some non-uniform circular motion. That's in 6.5b. But for now, we're looking at uniform circular motion, meaning that A equals v squared over r. That's centripetal acceleration, and it's a constant centripetal acceleration. The derivation of the centripetal acceleration equation, you can look at this if you want. You don't have to know how to do this one, so don't worry about that. But there it is for your perusal, if you like. The net centripetal force. Centripetal force is a net force. It's not an individual type of force. The centripetal force can be provided by the tension in the string, by friction, right? If you have a spinning turntable and a coin sitting on the turntable, a banked curve, right? A car going around a curve. If it's banked, that means it's at an incline. So the normal force is actually providing some of the centripetal force there. It could be a normal force, right? It could be if you're in the inside of like a cylinder, that ride where people stand against the inside of a barrel and it spins fast, the floor drops out. That's the normal force pushing on those people. Gravity, you can have a gravitational force holding a planet or a moon or a satellite in orbit, something like that. So now we're going to look at some applications of uniform circular motion. And so we're going to look at some different free body diagrams, some different views. So if we have a string, all right, string and rope problem. So the string is on, we have some mass at the end of a string. And so here the tension force is the centripetal force. So in this case we've got this circle. Here it is. Here's the object with the string. So in this case, here's the free body diagram. It just looks like this, Ft. So now the question is, what does it look like from the side? So when you're looking at it from the side, it's on the string like this. Well, from the side, that means that there is some force of gravity pulling down, and then there's some tension, this same tension here. So let me do Ft, is pulling that way. There's a question at the bottom, can the string in this scenario ever really be horizontal? The answer is no. There always has to be some vertical component to the tension in order to counteract the force of gravity. So no matter how fast this goes, it'll never be perfectly horizontal. So what are the plans here? Always draw a free body diagram, right? Always. free body diagram, or something like a free body diagram, even if it's not exact, because you want to look at the forces. You want to see what forces are involved. Resolve all the forces into radial and perpendicular to the radius accelerated tangential directions. In the tangential directions, right, the ups and downs, whatever, it's 0. In the radial direction, all the forces add up to m times AC, mass times the centripetal acceleration. And then you can solve for the unknowns. So here's another example, something a little bit more two-dimensional, and this is a conical pendulum. That's a conical pendulum, not a comical pendulum. It's one that's in the shape of a cone, not a pendulum that makes you laugh. So the side view here looks like this, right? And there's some angle theta here. Here's the tension. This is a tension force, and then you've got the force of gravity pulling down. All right, we're going to draw this again, but now what we're going to do is we're going to resolve this force. If I were solving this problem and I wanted to know, say, like, what's the tension in the string or something like that, well, what is the direction of the acceleration? As this thing is going around, right, it's a conical pendulum, so that means it's hanging and it's here. It's not swinging back and forth. It's swinging around like in a circle, and the string is tracing out the path of a cone. And so the center of the motion is this way. So I'm going to, this is going to be ft sine of theta, because theta is up here, right? We got to pay attention to that. And then this is the force of tension, ft cosine theta, up that way. And then this is the force of gravity. So if I know the mass, I can calculate what ft cosine theta is, and then I can calculate ft from that, right? And this is equal to m times AC, mass times the centripetal acceleration. Okay. Next, if I have friction on a flat horizontal surface, what does that look like? So looking from the top, this coin or whatever it is on the turntable. It's going around, and there is a force this way, and it is a friction force. The coin, whatever it is, just sitting there, and friction is what's holding it in. If there was no friction, it would just slide in a straight line off. From the side, let's say if it's a coin or something like that, it looks like this. The friction force is pulling towards the center, and you've got the force of gravity equal to the normal force in magnitude. Okay. The next one, B2. This is now someone is stuck to the wall, and if they're stuck to the wall, the question is then, what's the force that's pulling them in towards the center? That would be the normal force, Fn. And that, of course, would be equal to mv squared over r. So we could do something like this, like what's the speed that it has to go in order for someone to stay on the wall. Okay, well, what are the vertical forces here? The vertical forces are force of gravity, obviously pulling down, but what's the force then that's holding the person up, keeping the person from falling as the bottom drops out of this ride? And the answer is it's friction. It's a friction force, Ff. So that's mu, hopefully mu s, since they're not sliding, mu s Fn. You can see how you could calculate what v is, because this Fn is just mv squared over r. You calculate what v is from knowing what the force of gravity is, because this has to equal this. Okay, and so now this car example. Car with a banked curve. So it looks like this. Okay, and first we're going to look at this without friction. Okay, if there's no friction, that means that, okay, so what are the forces? We've got Fg pulling down this way. So the normal force is this way. So that's what Fg is, or Fn, right? This then is going to be Fn sine theta. And this has got to be Fn cosine theta. Right. Now notice what we're doing is we're doing the opposite of what we had done before, because before we resolved everything horizontal and perpendicular to the inclined plane. But here, since this thing is on a banked curve, right, it's coming around this way, and so this, what's the center of the circle? It's that way. This is the radial direction. So here's the direction of the acceleration, that way, right? I draw this off to the side, showing the direction of the acceleration. It's that way. So I resolve everything parallel and perpendicular to the direction of the acceleration. Now, what is this here, right? Fn, keep in mind that Fn is Fg divided by cosine theta. And so then this ends up being Fg tangent of theta. Right? And so then this is the centripetal force. And then now notice Fg is just mg, right? Mg tangent of theta is Fc. So that means that g tangent of theta is equal to v squared over r, or equal to ac in this situation. All right, so a little complicated there. But this is, you can see that you can keep a car on the track even without friction if you can get v to be the square root of rg tangent of theta. Now, C2, we're looking at this with friction as well. Now, whether or not there's friction, or what direction the friction is pushing, depends on how fast this thing is going, right? The free body diagram, so imagine here it's on the verge of sliding down. So what does this look like? Here's the car, and we've got the same forces we had before, Fg. This is Fn cosine or sine, this is Fn sine of theta. This is Fn cosine of theta. Right, we can figure that out by geometrical analysis, parallel lines and all that sort of thing. And so now the friction force is pushing up this way, Ff, and here's the angle. So that means that the vertical part of this is going to be the friction force Ff sine theta. And then pushing this way is Ff cosine theta. But we're going to imagine here that it's on the verge of sliding down. So that means it's going slow. Since it's going slowly, sorry, what am I doing here? Yeah. Since it's going slow, friction is holding it up. And so then this is actually going to be Ff cosine theta that way. All right, and so now, what are all the horizontal forces? Well, Fn sine theta minus Ff cosine theta equals m ac. The idea here, again, if it's going too slow, it'll slide down. And this is showing it where it's on the verge of sliding. That means friction has to be pushing up on it that way. Now let's take a look at the other one. This is C2, but on the next slide. Here it's on the verge of sliding up. That means it's going too fast. It's going really fast around the curve. And if it goes any faster, it'll slide up that way. If it's about to slide that way, that means that the friction force is pushing it downhill. So that's Ff. This then, if I break this up, it'll be pointing down and that way. So this now is Ff cosine theta, and this is Ff sine theta. Keep this in mind, like for the normal, these two things have to be equal to each other. This equals this. If it's moving just in a horizontal circle, these two things have to be equal. And so now, Fn sine theta plus Ff cosine theta is equal to MAC. Okay. Let's go right ahead and move on to the next thing. So now if we have non-uniform circular motion, that means that the v could be changing. But v is still, the instantaneous velocity is still 2 pi r over t. And some examples of non-uniform circular motion would be a merry-go-round, Ferris wheel, some of these things, vertical circles, right? A lot of vertical circle things. Things like those are uniform. Non-uniform would be a roller coaster, a diving airplane, a bucket being whirled around. So recall elevator problems, like the monkey situation. If there's downward acceleration, that means there has to be a larger net force down than there is up, down versus up. And if it's accelerating upward, then there is a larger upward force than there is downward force. Again, this doesn't tell us the direction of the motion, just the direction of the acceleration. So here, that's the direction of the acceleration. Here, that's the direction of the acceleration. So let's think about this for a minute as the bucket is whirling and it's at the top of the path. Right, so here's the bucket. It's got a string pulling down on it. We want to know the slowest speed that it can have. So here's v. If that's v, the direction of the acceleration is down. The slowest possible speed, then, there won't be any tension in the string. It means if there's no tension in the string, the only force pulling downward on it is this, Fg. So if this is the only force, Fg is equal to mac. This is providing the centripetal acceleration. So mg equals mv squared over r. M cancels out. And v is the square root of gr. Right? Or if we switch the g and the r, we get radical rug. Right, so that's scenario 1. Scenario 2, vertical circles and strings. Right, things that you should already know. If we have a mass at the end of a string moving in a vertical circle, a couple of things. It will always move faster at the bottom than at the top. Always moves faster at the bottom. Why? Because as it's coming down, it has gravity accelerating it downward. That means the tension in the string is greatest at the bottom, and it's always least at the top. So when we're doing these types of problems, always, again, draw the free body diagram. Break the vectors into centripetal and tangential components. Use sigma f equals mac for the centripetal acceleration. And now we're also going to have some tangential acceleration, which we can calculate using sigma f tangential equals ma tangential. And we're just splitting everything up. So, let's see. What does this look like? The free body diagram then. So if I have a string going around like this, then this is the direction of the tension. This is the direction of the force of gravity. And so the direction of the acceleration is that way. Here's the tension. So I want to know, what I'm going to do then is I'm going to break up Fg into some components here, right? So let's redraw this where we can break this down. Here it is. That's the tension and the direction of the acceleration. And so here's the force of gravity. If this is some angle theta, then this is Fg cosine theta, and this is Fg g sine theta, right? Going that way. And so let me redraw this again. So here's Fg cosine theta. Here's Fg sine theta. Again, where theta was the angle with the vertical that it's making here as well. All right. So the net force Fc equals mac. And so this is T minus Fg cosine theta equals mv squared over r. All right, and what about the tangential? Sigma f tangential equals ma tangential. All right, and then this is the only force in the tangential direction, right? Fg sine theta. So, and Fg is mg, so mg sine theta equals ma tangential. This cancels out, so a tangential is just equal to g sine of theta. All right, so now we can take this and we can apply this. What if theta is 0 degrees? Theta being 0 degrees would mean that it's hanging straight down. All right, so in this case, a tan is 0. Right. And in this case, AC would be, let's see, so if this is 0, this would be just T minus Fg. That means T has to be really big because it's counteracting FG. What if it's at 90 degrees, right? So it's over here, like that way. Here, A tan is G. Oh, sorry, this would be over M, by the way. So A tan equals G in this case, because it's pointing down. And then the centripetal acceleration is just going to be T over M. Right? What if it's off to the side this way? Again, same thing. So these answers apply here and here. And what if it's at the top? Right, it's up like that. In that case, A tan is going to be, again, 0. There's no force. And AC is going to be T plus FG, because in this case, they're both pulling in the same direction over M. Okay. All right. Vertical arc problems, right? All these are, again, just like elevators. If you have so the first one, if you've got the car going over a hill, or the roller coaster over a hill, or the airplane going over something, in that case, what direction is the acceleration? It's down, right? That means you've got the force of gravity, which is greater than the normal force. Or in the case of an airplane, it would be a difference of pressure providing the force. Okay, and then what about in the next one? So when we have downward centripetal acceleration, when you have an upside down roller coaster. The upside down roller coaster, there the normal force is actually pushing down. Right, as long as it's going fast enough. If it's not going fast enough, then there's no normal force. It's like the whirling bucket problem we had before. And then what about when you're at the bottom of a curve? All right, if I have a roller coaster car or an airplane at the bottom of a curve, so something like this, like what's in the packet, in that case the direction of the acceleration is upward. That means that whatever the force of gravity is, the normal force has to be greater. So it's at times like this on a roller coaster where you feel heavier. If you're putting your hands up in the air, it's actually harder to keep your hands in the air at times like this because the seat is pushing up on you more and you feel heavy. What you feel actually is not the force of gravity. What you feel is the earth supporting you underneath, right? And the weight of your body on the bones. So when you're at the top of a hill on a roller coaster car, right, you actually feel lighter because the seat is pulling on you less, right? Remember this? What we just looked at, the normal force is less than the force of gravity. So you feel lighter than you are. Here you feel heavier than you are. All right, so let's take a look at this roller coaster car that's going around and up and down on a roller coaster, and it's going around. So the different points, we're just going to draw what direction the acceleration is. At point A, right, it's coming around the curve, and so the direction of the acceleration is towards the center of the curve. That's it. At point B, it's at the bottom of a dip, right? So there, the direction of the acceleration is upward. At C, it's at the top of a hill, so the direction of acceleration is down. D, it's at the bottom of a dip, so the direction of acceleration is up. At point E, it's coming around the curve, right, going around the other side. So at point E, the direction of acceleration is to our left as we look at this. F, it's at the bottom of a dip, so the acceleration is upward. G, it's at top of a hill, so the direction of acceleration is downward. And then at point H, it's at the bottom of a dip again, so the direction of acceleration is upward. Okay. And the rest of this now is just looking at any other problems that we're going to see is using these free body diagrams and drawing the diagrams and writing the equations and using Newton's laws to solve. And they'll be combined in all kinds of ways. You'll be amazed at how complicated it can get. But just keep the basic ideas in mind. Draw the picture, separate everything into the radial and tangential directions, and set up Newton's laws equations, and you should be able to do it. Okay, welcome to Unit 4. We're going to be studying drag, resistive forces. We've held on to this until now because, not in this lecture, but in the next one, we're getting into some pretty heavy calculus, some integration. So this one's pretty easy, this one's pretty short. And then after drag, we're going to get into momentum and center of mass using calculus. Right. So let's just get into it now. So 6.4b, day 1. Most of the time in first year physics, you did not take drag into account. You didn't take air resistance into account. Everything was just no air resistance. In the real world, there is air resistance. And even though we still do a lot of things in our magical, imaginary physics land, and it's all theory, we do want to look at least the theory of air resistance and air drag and see how it works. So without air resistance, the graphs for position, velocity, and acceleration versus time look like this. If down is positive, by the way, right? So down is positive. That's what we have. Constant acceleration, constantly increasing velocity, so a straight line, and a parabolic curve for the position as a function of time. But with air resistance, it's different, right? When you're dealing with high speeds, generally, the amount of drag force that's there is proportional to the square of the velocity. And this is the Crave equation that's on your packet, right? D equals 1/2 Crave, C rho A V squared. And it's, don't forget the 1/2, right? So D, this is the force of drag, the drag force. That's what D stands for. Equals C rho, or 1/2 C rho A V squared. So it's Crave, but don't forget the half and the squared at the end. C is the coefficient of air resistance. And this depends on the fluid through which the thing is moving and the nature of the surface itself. So it's a very smooth surface, that'll be less, right? If it's a very rough surface, so something like a tennis ball, it's more. Rho is the density of the object, or the density of it's the density of the air where it is. Density of the environment, the fluid, whatever it is. And then A is the cross-sectional area of the object. So if we have something that's spherical, that's falling, what we care about, A, represents this, we'd have to find the area of this circle here as it's falling. Okay, that horizontal cross-sectional area. And then V obviously is the velocity, right? So the force varies, the drag force varies as a function of time. One of the things we're going to be doing here is finding what is the terminal velocity. As things fall, the drag force increases, and at some point we reach a place where the force of gravity is equal to the drag force. At this point now, it reaches velocity and it just stays there. It's not going to increase anymore. There's no more acceleration because these two forces are equal. The net force is 0. So when something is first dropped, force of gravity is pulling on it. It has no velocity, and so that's what the free body diagram looks like. As it's speeding up, here's the force of gravity, but the drag force is less than this. That means this is still accelerating. And then at some point it gets to this place where these two forces cancel out. The acceleration graph then is going to look something like this. Acceleration versus time. We're going to get into that a lot more in the next lecture, but just so you can see it now, that's what it looks like. And so if I know this, though, if I'm asking about the terminal velocity, at terminal velocity, that's when Fg is equal to Fd. When the gravitational force is equal to the drag force, that means that the gravitational force is equal to 1/2 C rho A V squared. So if I know C rho and A, then I can solve for V if I know what Fg is, if I know the mass of the object, if I know the weight of it. Okay, and that's what our first example is. Here we have example 1, a falling cat. Why a cat? I don't know. Falling cat reaches a terminal speed of 97 kilometers per hour while it is tucked in and then stretches out, doubling A. So how fast is it moving when it reaches a new terminal speed? So we know the terminal speed at one time. Now we want to know what's the terminal speed at another time if this doubles. Right. And so we have one value for V. So V, what is V equal to? V is equal to 2 Fg over C rho A, the square root of that. Right, but what I'm doing now is I'm doubling A. This I know is equal to 97 kilometers per hour. But when I double A, that means I'm multiplying this by 1 over root 2. Okay, so 97 times the square root of 1/2 is 68.6 kilometers per hour. Okay, don't need to know anything else there, just knowing how A, the cross-sectional area, is proportional to the velocity, which we can solve for from this equation and find. Okay. Next example is a little bit more involved. Okay, so here I want to know, what is the terminal speed of this drop given these conditions? Well, if I solve for v like I did before, we're talking about terminal speed, so we're talking about the place here where the drag force is equal to the gravitational force. So I plug in gravitational force. When I solve for v, I end up with 2 Fg over c rho a, where rho is this, the rho of air. And so in order to find Fg, though, I need to know the mass. And I can get the mass from using this information here. So I know that rho of water is equal to the mass per volume. Right? And I know the volume of this thing. The volume I can calculate from R. So M is equal to R, which is 1.5 times 10 to the, rho. Rho is 1.2 or 1,000 kilograms per cubic meter. And the volume of this drop is 4/3 pi r cubed, and r is 1.5 times 10 to the negative third. So we're going to cube that. Okay. So then this tells me that the force of gravity, multiply this by 10, I'm going to 1.39 times 10 to the negative fourth. I also need to know the cross-sectional area. So area is 2 pi r. R is 1.5 times 10 to the negative third. Rather, A is pi r squared, sorry. And so this is 7.06 times 10 to the negative sixth square meters. This is in newtons. So I plug these numbers in here, and so I get 2 times the square root of all this, 2 times 1.39 times 10 to the negative third, or 10 to the negative fourth, sorry, looked at the wrong line over there, over C, which is 0.6, times rho of air, which is 1.2, and then A, which is 7.06 times 10 to the negative sixth. Right? And when you put all that in, what we end up with is 7.15 meters per second. Right, so it's really not moving all that fast. But let's see what it would be like if there was no air resistance. If there is no air resistance for part B, we're just using VFTAD, so we can say that VF squared equals 2A delta Y. A is G in this case. Right, so V is going to be the square root of 2 times 10 times, and it's dropped from 1,200 meters. This comes out to 153 meters per second. So it's a lot nicer to be outside in the rain when the raindrops are moving 7.15 meters per second instead of 153 meters per second. And that's it for this lesson. Okay, welcome to day 2 of drag and resistive forces. Drag was kind of what we did before. Now we're going to talk about resistive forces. This is typically lower speeds, things like that. But buckle up, because this is maybe one of the hardest lessons. Later on in the year, this won't be so bad because you'll know the calculus more. You're going to be seeing it for the first time today, and people say this is one of the toughest lessons for them because of the calculus that we're doing that's involved. So, just some kind of review in order for us to figure out what's going on, because we're going to be dealing with exponentials. If we have 4 equals e to the negative t, right, how would we solve this if we were to try to solve for t? The way that we solve this is we take the natural log of both sides. So I take the natural log of 4, so natural log of 4 equals, and when I take the natural log of e to the negative t comes down in front. Right? So this is negative t, natural log of e, but natural log of e is just 1. So natural log of 4, sorry, let's try that again. Natural log of 4 is negative t. And so what this comes out to, t is negative natural log of 4, which is 1.39, negative 1.39. Okay? Pretty simple, right? For the next one, 0.5 equals e to the negative t. Well, then we have natural log of 0.5 equals negative t. So that means t is the negative of this, and we get 0.69. Okay. This should not be hard yet, by the way. This should be pretty simple stuff. See, we're looking at 0.5 equals e to the negative 5t. Okay, so now we have a coefficient on the t in the exponent. So how does this change things? We end up with natural log of 0.5 equals negative 5t. So that means t is equal to negative 1 over 5 natural log of 0.5. So it's like I'm taking this. Sorry, this should have been negative. It's like I'm taking this and I'm just dividing by 5. So this ends up as 1.39. And this should not be negative, actually. This is going to be positive, right? Because in order to get 0.5, e to the what will give me 0.5? Well, 0.5 is less than e, and so it has to be a negative exponent. So it's a negative of a negative, and we get that thing, right? Think of logs as just backwards exponents. E to the what power will give me this number, and the what power, that's your answer. Same thing here, right? E to what power will give me 0.5, and then I multiply that by negative 1.5. And so this one should actually end up being negative, because this will be positive, sorry, it all works out. Good. D. So now we have another thing, so 0.5 equals e to the negative 2t over 5. All right, we're working out because we're going to have this type of thing in our equations here, and we're going to be doing calculus with it. So you see it's piling up. So this is going to be natural log of 0.5 equals negative 2/5 t. That means t is going to be negative 5/2 natural log of 0.5. Yeah. And then this ends up being 1.7. Okay, good. So that's good in terms of calculations. Now let's look at some graphs of these things and see how this works. Okay. If I have y equals e to the t, what does that look like? Right, that's going to look something like this. It's going up. But if I have y e to the negative t, that means I'm starting off here. If this were 0, this would just be 1, right? But as t gets bigger, this value is going to decrease. So it actually looks like this, right? This is an asymptote to 0. So now let's try this next thing. If y equals g e to the negative b over m times t, you're going to see that's going to become very familiar. This, instead of being 1, it's going to start at this value of g. Okay, and then this is negative, so it's still going to be going down like this. It's going to be asymptotic to that. If I look at y equals negative e to the t, so we're putting a negative in front, that just looks like this. I drew the graph the wrong way. Right, like the graph we had before, just flipped over the horizontal axis. And then, but if y equals negative e to the negative t, that's going to look like this, right? But if instead of starting at 0, or rather starting at 1, if I say that y equals 1 minus e to the negative t, then this starts off at 1 and gets closer to 0. So this whole thing is going to get closer to 1. So this is 1. This is going to look like this. All right. But now, if I take this same thing, and instead of having 1 there, I have some coefficient in front, like alpha, then this just replaces alpha, and it's approaching this value of alpha as time goes on. All right. And then, so kind of like we had before, if instead of alpha I have something like, I don't know, mg over b, minus e to the negative b over m times t. So now I have a coefficient on this, but that's not going to affect the fact that this is still getting closer and closer to 0 as time goes on. And this is 1, but I'm starting, instead of starting at 1, or going to 1, I'm going to mg over b. That's my asymptote there.
Sadiq,
Hey,
I got my microphone, so are you recording a lesson?
I am.
Oh, sorry.
That's right. I can pause it. Say hi to Mr. E, everybody.
Hey, Mr. E, are these my AP Physics C kids?
Yes, they are.
Love you.
All right, so we're going to look at these equations of motion. We're going to derive these, and then we're going to be using them again and again. It gets complicated, but it's the same process that you do again and again and again. So just when you're learning it, go through and follow the steps, and then eventually you'll be doing the same thing. And we're going to use this now, we're going to use it later, same process. So what we end up with is if we imagine something, you know, falling down, and it's reaching its terminal velocity, or whatever it is, as it's speeding up. This is mg, and this is r. Let's call it r for now. So mg minus r equals ma, mass times the acceleration. The acceleration is down, so I'm going to make down positive here. If I substitute in here, so here r equals negative bv, right? So mg minus bv equals m. Now I'm going to put this in terms of v. So this a is dv dt, right? So what I'm going to do now is divide by m. So I get g minus bv over m equals dv dt. Right. This now is what we call a differential equation. And watch what happens. I'm going to bring dt over to this side. Since v is here and v is here, I want to get this v with this v over here. So I'm going to divide everything over here. I'm going to say, so I'll put dt on this side, multiply dt over to this side, equals 1 over g minus bv over m times dv. If I were to solve this differential equation, right, I integrate both sides. So integrate this side dt, integrate this side. Then what I would end up with is what we have on the next side. All right, that vt, v is a function of time, is 1 minus mg over b, 1 minus e to the negative b over m times t. And we're going to see that form of the equation again and again and again. So get used to it. So what are the units of the quantity b? Well, b over m, this has to cancel out and have no units, right? Or rather have units of time. So this is being divided by kilograms and multiplied by time. So b has units of kilograms per second. All right, so what happens when t is equal to mb? When t is equal to mb, then this whole thing is equal to 1. Okay, that's what we call one time constant. We're going to have at one time, you'll see how that plays in. So just pay attention to that. And then we call that time it takes. So what do we call that time? We call it one time constant. There it is. That's the answer to that question. And then here's the derivation, how we get that in the first place. Right? Taking a look at taking the derivative, we have acceleration. Acceleration is dv dt. So if we take the time derivative of this, then we end up with a equals g e to the negative b over m times t. So what does this mean? This means here that when a is equal to, or at the initial time at time 0, this whole thing is equal to just 1. Right? So at the initial time, g is equal to, or the acceleration is equal to g. But then as time goes on, this whole thing gets smaller and smaller. Right? What's happening here? At initial time, this is 1. So this starts off at 0. That makes sense. The initial velocity is 0. But as time goes on, the velocity reaches a certain, it's going to reach a certain maximum velocity, which is mg over b, right? Because this whole thing on the inside then is getting closer to 1. Right? As this goes to 0, this gets closer to 1, so 1 times this. So the velocity time graph, I think that's what we have. The velocity time graph, yeah, mg over b looks like this. And the acceleration versus time graph looks like this. Starts off at g. So whatever the coefficient is, that's either your initial value or it's your asymptote. If the equation is this form, where it's not 1 minus, it's just e to the whatever, then it's going asymptotically to 0. But if it's of this form, 1 minus e, then this is the asymptote. It's coming up to that. Right? So you're going to see these two forms again and again here and in the future, so get used to that. So example 1, a small sphere of mass 0.002 kilograms is released from rest in a large vessel filled with oil. The sphere has a terminal velocity of 0.05 meters per second. Calculate the time constant. So remember, the time constant is just the that b over m thing. I don't know what b is because I got to do this first. R equals bv, that's the resistive force. But what we're saying here is that the resistance force is equal to the force of gravity. Right? So this is going to be mg equals bv, and so b is going to be equal to mg over v. mg is going to be, this thing has a mass of 0.002 kilograms, and the velocity, so 0.05, so 0.02 newtons over 0.05 meters per second. So b is going to be 196. Right, so that's part A. For part B, now I want to know, calculate the time it takes to reach 90% of v term. Okay, so what does that mean? So v is equal to, now the terminal velocity is whatever it is. We don't even really need to know because we're saying that we're reaching 90% of it. So I've got some v term here. That's what this is. And this is 1 minus e to the negative b over m times t. But this is going to be 90% of this. So if I do 0.9 v term equals v term 1 minus e to the negative 196 t, v term goes away. And now I'm just solving for t. Right? And how do we solve for t? Well, we solve it by taking the natural log of both sides. So natural log of 0.9 equals 1 minus e to the negative, so first thing I actually have to do, I'm not ready to solve it yet, I need to subtract 1 from both sides. So I end up with 0.1 equals negative e to the negative 196 times t. Right, you see how that works? So I do, or rather 0.9 minus 1, so I get negative 0.1. And then this is negative, so they cancel out. It's just arithmetic. And then So natural log of 0.1 equals negative 196 times t. And so t is equal to negative 1 over 196 natural log of 0.1. And that turns out to be 0.0117 seconds. So in 12/10ths of a second, this has already reached 90% of V term. So it's slowing down very fast. All right, what about the time it takes to reach 95%? Well, if I've got 95%, if this is 0.95, let's go back to this place. If this is 0.95, that means I'm doing 0.95 minus 1. So instead of this being 0.1, it's going to be 0.05, right? So for C, it's going to be natural log of 0.05 equals negative 196t. So if I repeat this, instead of 0.1, I put in 0.05, then I end up with a time of 0.0153 seconds, right? So more time goes on, it gets slower, or rather it doesn't get slower, it gets faster, but it gets that much closer to V term. And then question D asks, when does it reach 99.999% of V term? Okay, so this is annoying because if I put in, point, and this is 5 nines, right? So 0.99999, and I do that minus 1, what I end up with is natural log of 0.12345 equals negative 196t. But if I do this same calculation, I just put in here, 0.000001, with that many ones, then I end up with t equals 0.587 seconds. Okay. All right, so now we're going to get into some, these are real AP problems, right, and there are 3 of them. How much time do we already have on this video? Might have to cut this into 2 videos. Okay, so now we're going to look at some real AP problems. This is from 1993. It says a car of mass m, initially at rest at time t equals 0, is driven to the right as shown above. Okay, and it says the car encounters a resistive force equal to negative kV. It's like we had before, except instead of B, we have K. Same thing, just using a different letter. And now we want to know, A, the dot below represents the center of mass of the car. Draw and label vectors to represent the forces acting on the car as it moves with a velocity v to the right. So this is what this should look like. It says as a velocity v to the right. They're not necessarily saying that it's at terminal velocity, but it is moving. And so here is the force of the car, which we can call F naught, the constant force. That's it pushing to the right, F naught. The resistive force is kV. Don't forget the force of gravity. And then equal to the force of gravity but opposite in direction is the normal force. That's it. Now let me tell you something about the AP test. Each open-ended question is worth 15 points. And those 15 points are distributed to the different parts of the question. So this part A, if you do this, that's 3 points. You've already gotten 3 out of the 15 points just for doing a good free body diagram. Right? Make sure the arrows connect, etc. Follow the rules. That's it. So now we want to know the horizontal acceleration of the car in terms of kv, f naught, and m. Okay. So what does that look like? Well, if we're determining acceleration, we're going to have to get that from Newton's second law. And so the sum of the forces, so this is F, what direction is the acceleration going to be? The acceleration is going to be backwards, right, in the direction of the, because it's going to be slowing down. Or no, it's not. Sorry, it's speeding up. This is speeding up. So the change in acceleration is in the other direction. But this is speeding up, so it's in the direction of F naught. So I'm going to do F naught minus kV equals ma. So I want to find the acceleration. Well, the acceleration is F naught minus kV over m. And that's it. That's all we have to do. That also was worth 3 points. Right? So if you did the free body diagram correctly and you did this correctly, then you've got 6 points already out of 15 on this question. Okay, C, derive the equation expressing the velocity of the car as a function of time in terms of K, F naught, and M. Right. This one gets really tricky. This one involves the crazy calculus. So what happens is this now becomes, let me rewrite this. Except instead of A, I'm going to write dv dt. So this is F naught minus kv over m. Okay, and so now, how am I going to get a function for velocity? Here's what we have to do. What we have to do is actually separate these. I'm going to keep v on this side, and I'm going to put t over on this side. Right. So I'm going to have, I'm going to bring this, since this thing contains v, I'm going to bring this over, so I divide. So this is going to be m over f naught minus kv dv equals dt. So how do I get from dv to actually be v and t to actually be t, right? Some function involved there. Well, what I have to do is integrate. So I'm going to integrate this side from 0 to some velocity, some later velocity. And here I'm going to go from time 0 to some later time t. In calculus, you're not really supposed to do that. But here, we're putting in variables because we want an equation expressing the velocity as a function of time. So we're going to have a changing time. What is this final time? We don't know. What is this final velocity? We don't know. And so this is easy to integrate, right? This would just be t. But this looks pretty weird, right? How do we do this? What we have to do is we have to think of this as backwards chain rule derivation, right? It's the antiderivative, but we've got like something inside of another function. And so it's like using the chain rule. Now I know that the derivative, the antiderivative of 1 over v is natural log of v, but that's not going to work here because I don't just have v, I have this whole thing. But if I can get this as one variable, then I can do that. So let me take this, f naught minus kv. I'm going to set this equal to just u. Okay, so now I've got f naught minus kv equals u, so I can plug u into this. However, if I plug u in here, then I don't have the v. I've got dv. So I need to replace dv with something. So I go back down here, and I'm going to take the derivative of this with respect to v. So du dv, I take the derivative of this with respect to v, I end up with negative k. That means that du, or negative 1 over k du, is equal to dv. Now I can substitute this in for dv. Right? This will go in here, and this will go in here. So what does this new thing look like now? From 0 to v, whatever that later v is going to be m over u, right? And now I'm substituting this thing in, so this is negative 1 over k times du equals integral 0 to t of dt. Let me bring this thing out in front. Notice now I've got negative m over k. Does that look familiar? Negative m over b. So that's interesting. Integral from 0 to v of 1 over u du equals integral from 0 to t of dt. Let me move up here now. Now I can do this. I know this is natural log of u. Right? So this becomes negative m over k, natural log of u, from 0 to v. And then this is equals, this ends up just becoming t. Sorry, that shouldn't be that simple. It would be this, from 0 to v. Now I'm going to bring this over to here. So I've got natural log of u equals negative k over m times t. Now how do I get rid of a natural log? Right, the way I get rid of this is that I exponentiate both sides. I put both sides to the power of e, right? So e to the this thing is just u. So u equals e to the negative k over m times t. But what was u? U is equal to this thing, right? F naught minus kV. So this is F naught minus kV. I'm still going, by the way, from 0 to V. Or rather, let me plug this back into here before I do anything else. Sorry. So natural log of, this is going to be F naught minus kV from 0 to V equals negative k over m times t. So if I do natural log of, I plug v into this, F naught minus kV, minus natural log, if I plug 0 in, then I just end up with F naught equals negative k over m times t. Subtraction, though, means I can put this over this. So I get natural log of F naught minus kV over F naught equals negative k over m times t. So this can go out of there, and this just becomes natural log of 1 minus k over F naught times v equals negative k over m times t. Good. Now what I'll do is I'll take both sides, e to both sides. Oh yeah, okay. Let's see how this works. So this becomes 1 minus k over F naught times v equals e to the negative k over m times t. So I'm going to subtract 1 from this side, or rather, if I leave it, k over F naught v equals, I'll do 1 minus e to the negative k over m times t. And now I bring this over, so v equals F naught over k, 1 minus e to the negative k over m times t. That's it. That's my function now for velocity as a function of time. That was a lot, right? I realized that, but look at what we started with. Differential equation. All we did was we substituted in for u. So we substituted in for this thing, and we substituted in for this thing. So it's backwards chain rule, right? Now I simplify it, I integrate, and now all I'm trying to do is plug v back in here, and then solve for v. So I do all this stuff, and I'm using a lot of my math tools. If it was tricky, here's what I would say. Put this away, and then try it again. Look back to help yourself, because it's just going to be this same process again and again. The reason we have to use the u substitution, by the way, is because I've got a function down in here. Right? Why do I have this function? Because I have a constant force on the car that's pushing it forward. Right? So then that's worth 5 points. All of this is worth 5 points. Worth, parts D and E down on those other slides, these are worth 2 points each. All right, well, what do these look like? For part D, they want the car's velocity as a function of time. So we saw that coefficient in the very front was F naught over K. So it looks like that. That's velocity as a function of time. The other one asks for the acceleration as a function of time. And it says label the important values. So this is F naught over m. That's the initial acceleration. Because when we plug 0 in for the velocity, then a is just F naught over m. And this looks like this. The acceleration is going to 0. So 2 points, 2 points. Let's take a look at another question here. So this is a question from 2000. By the way, this 1993 question was Mechanics 2. That means it's the second question. Usually they get harder So the first one's the easiest, second one's the next hardest, and then so you can see what the level of difficulty is sometimes. But again, you're not doing new stuff. It's like the same process you've done over and over. So now a rubber ball of mass m is dropped from a cliff. As it falls, there is air drag. The force is bv squared. So that's the drag force, bv squared. It's not kv like the other one we had before. The drag coefficient b is directly proportional to the cross-sectional area of the ball. So this is like what we did in the first lesson. And as the ball falls, its speed approaches a constant value called the terminal speed. Okay, so now we need to do a free body diagram. It says draw and label all the forces the instant before it reaches terminal speed. Some instant before it reaches terminal speed. So some instant before terminal speed, that means this resistive force arrow is less than this force of gravity. It hasn't reached terminal speed yet. That means this is not the same length as this. Okay, so now state whether the magnitude of the acceleration increases, decreases, or remains zero, remains the same as the ball approaches terminal speed. Here's the idea. Since sigma f equals ma, mg minus bv squared equals ma, initially at time 0, the acceleration is just equal to g. But as time goes on and this gets faster and faster, that means a gets less. This value gets more. This whole thing gets less. That means a has to get less. So a decreases over time as v increases. And you can use some argument like that. Again, this is 3 points. This would be worth 3 out of the 15 points. C says write but do not solve a differential equation for the instantaneous speed of the ball in terms of time t, the given quantities, and fundamental constants. All right, so now I'm taking this and I'm turning this into a differential equation. The differential equation means it's like dv dt. That's it. So this is mg minus bv squared over m equals dv dt. That's the differential equation. It says do not solve it. Solving was that other thing that we did with the previous example. So done. D, determine the terminal speed v in terms of the given quantities and fundamental constants. So at terminal velocity, so what is this, part D now? At terminal velocity, that's where the acceleration is 0. So mg minus bv squared equals 0. So I'm solving for v. So v is equal to mg over b, and then the square root of that. So that's it for that one. And it says determine the energy dissipated by the drag force during the fall if the ball is released at height h and reaches its terminal speed before hitting the ground in terms of given fundamental given quantities and fundamental constants. All right, so now we're going to use GAPSI. Right, so we've got K plus U plus the work done by non-conservative forces plus the work done by applied forces equals the kinetic energy at the end and the potential energy at the end. So initially there's no kinetic energy, there's no work done by outside forces, Earth, but that's part of the system, so that's in here. And then there's work done by non-conservative forces, that's what we're looking for because that's what the air resistance is. And then when it hits the ground, there's no more potential energy. Right? So what is our potential energy? It's dropped from height h, so this is mgh, plus the work done by non-conservative forces, equal to, and then I want to know the final. So this is 1/2 mv term squared. Right, that's the terminal velocity. But notice I solved for that here. So that's going to be kind of nice. So the work done by the air resistance is going to be 1/2 m times this thing squared. So this is mg over b. And then minus mgh. So the work done by air resistance, I can bring out an mg, and then I've got, so this is now another m over 2b minus h. And that's it. Okay, so using GAPSI now in solving a problem like that. All right. This next one we have a block of mass m, Initially, it's moving with a velocity. So it's moving with velocity v naught at time 0. And then there is a resistive force on it, given by kV. And how much work must be done to bring the block to rest, etc. Okay, so here's the idea. The block initially is moving this way, v naught, but there's this force on it. It's pushing it back that way and slowing it down. So what does the velocity graph look like here? It looks something like this. Right, that's v naught, and v naught, v is approaching 0. All right. That means that at some later time, it has 0 kinetic energy. So it's starting off with kinetic energy. And K is equal to 1/2 mv squared. So the work done by the friction force is just equal to negative 1/2 mv naught squared. The force is doing negative work. Why is the force doing negative work? Because the force is that way, but the displacement is that way. Right? You think of it that way. And the work is taking away that much kinetic energy. For B now, it says that if the force is negative kV, right, so the opposite direction of V and then times K, determine the following. The acceleration of the block in terms of M, K, and V. All right. So here, this is the only horizontal force. So kV equals ma. This is the drag force, and that's equal to ma. Right? This is the force mass times acceleration. So that means that A is equal to kV over m, and that's it. Or the negative rather. Don't forget the negative. So this should be negative here. Because the acceleration is in the opposite direction of the velocity, so if we're expressing these as vectors, we include that. Now I want to know, part C, it says the speed v as a function of time. So now we need to do this whole thing where this is dv dt equals negative kv over m. All right, so what I'm going to do now is I'm going to bring the v over to this side. I'm going to leave the other things, though, over here. Notice here it's just v. There are no other terms here, right? In the other one, I had the term f naught. Now there are no other terms. It's just this one term. So I'm going to do 1 over v dv equals negative k over m times t. I couldn't set this one up before in the other one. I couldn't set it up like this. But now I can because of this, just having this one term, because there are no other forces here. Right? That's why I end up just with this. So now I have to take the integral from 0 to v of 1 over v dv, and that's equal to the integral of negative k over m times t from 0 to some later time t. This becomes natural log of v from 0 to v, and this is negative k over m t. When I put in, so this becomes natural log of v minus natural log of 0. So this is 1, actually, right? Equals negative k over m times t. E to the what power is 0? Or no, sorry. I'm not going to 0. Aha. Tricky. What's my initial velocity here? My initial velocity is v naught. It's not 0. So this becomes v natural log of v over v naught, negative k over m times t. That's important. Paying attention to what are our initial conditions there. So this now, when I take e both sides to the power of e, or e to the power of both sides, I get v over v naught equals e to the negative k over m times t. So v equals v naught e to the negative k over m times t. Okay, and so that's it. Initially, this thing, if this is 0, that means this whole thing is 1, so v equals v naught at time 0. And then as time goes on, this gets closer and closer to 0. Theoretically, it never actually reaches 0. Right? But in practice, there are things of different grades. The friction force is constantly changing. It does actually reach 0. So this graph looks like, just looks like this. already drew it. And then the last part, we want to know the total distance that this goes. Okay, if I have a velocity function, how do I get displacement? Well, I get displacement by integrating. So v, rather the change in position, so let's say delta x, is from 0 to infinity. I have to go all the way out to infinity where this thing actually stops. So from 0 to infinity, v naught e to the negative k over m times t. All right. So this ends up becoming v naught. I take the integral of this. So in other words, the derivative of what would give me this, it's going to be negative m over k e to the negative k over m times t from 0 to infinity. So let me pull this out. Negative v naught m over k. And now if I plug in infinity into this, then this whole thing, right, this goes to e to the negative infinity is just 0. Right, this goes to 0. Oh yeah, because it's getting smaller and smaller. If I plug 0 into that, I get 1. So I get negative 1, so it's just v naught m over k. That's the total distance that it travels. Okay. Again, I realize it's a lot. This is not easy, but it's still this same kind of thing over and over again. So you get used to the process and you do it again and again. And keep in mind when you need to do U substitution. You have to do U substitution when you've got more than one force, right? You've got the resistive force and you've got some other force like gravity or some constant force like we had on the car. In this case, we don't have to do U substitution. Why not? Because there's only one force in that direction, and that's the resistive force.
So if you've made it this far, congratulations. Don't forget to like and subscribe and share.